Okay, guys, 2025 Probe 1 Fall questions 16 through 20. So let's just jump into it. Question 16. Justin cooks a batch of brownies for his three kids. He slices them into a 5x8 grid. Okay, a 5x8 grid. Okay. However, his kids do not like the outside pieces with the crust, and so Justin and his friends eat them. If he divides the inside pieces evenly among his kids, how much does each one get? Okay. So I'm just making this grid here. Is this a 5x8? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 5. Yes, this is a 5x8 grid. And this is like the brownie pan. Okay. But we're cutting off the outside pieces with the crust. So all these ones gotta go. Gotta go. The kids ain't gonna eat them. So that leaves us with this 1, 2, 3, 4, 5, 6, 3x6 grid of brownies, which is going to give us a total of 18 brownies. And we're dividing them among his three kids evenly. So we're just going to go ahead and divide this to get 6 brownies per kid. So our answer is A. Nice. Question 17. A fair 6-sided die has the numbers 1, 2, and 3 written twice on it. If you roll the die 4 times, what is the probability that you will, at some point, have rolled the same number twice in a row? Okay, so it's difficult to think about how many different ways there are to have rolled the same number twice in a row at least once in like a set of 4 rolls. So how many total rolls are there in the first place? We have 3 options per roll, and we're rolling 4 times, so that gives us 81 total options, because 3 to the 4th is 81. So there are 81 total. It says total. And then we want to find how many we succeed in getting the same number twice in a row, at least one time. So that could look like 1, 1, 2, 3, or 1, 2, 2, 2, right? Because in both these circumstances, at least once it's true that we have the same number twice in a row. Okay, now there are different ways that you could think about the casework here, because it is going to be casework. There's no, like, you can't just say I have this many rolls, this many possibilities, then this many, then this many, then this many. It's not going to work like that because of how different the ways to actually succeed are, right? If you just say I want, like, if you go into it like there are 3 possibilities and then I want the second one to be the same roll, so I have 1 possibility and then the other 2 are free. That doesn't capture everything because first of all, it doesn't necessarily have to be the first and the second that match up. And also, if, for example, you get to the point where you're doing like, okay, this is free to do whatever, and then I want in the middle to be when it occurs, right? So 3 times 3 times 3 times 1, because we want that one to be fixed, times 3. That's also not going to capture everything because it's possible here for these two to have been, the same. So you might try and rectify that by being like 3 times 2 um times 1 times 3. But the problem is that there's going to be overcounting because for every time that you've counted that, when you move on to the next step, you're going to have to consider all the cases that you've already counted, and it's just a whole bunch of casework. I would much rather just do a problem like, okay, what if we never roll the same number twice in a row? So then we would have 3 options for our first roll, and then our next roll would only have 2 options, right? So, and then our roll after that would also only have 2 options because we can't have the same roll as before, but that's our only constraint, right? So we're free to have any of the other 2 that we didn't just roll. So that's true for the next 3 rolls after the first one. So that gives us a total of, what is that, 24? Unfortunately, that's not what the problem is asking for. It's not asking for how many times we fail. It's how many times we succeed. But wait a second, we can either fail or succeed. So out of the total, right, 81 times, it's each time is either a success or a failure. So there are 21 failures. That means that the other 57, right, 81 minus 24 is 57. Those all have to be successes. So that means there are 57 ways to succeed. We didn't even have to compute any of the cases, right? There are 57. We didn't count any of them. There are 57 ways to do it. We know that for sure because there are 24 ways to fail, and you either succeed or fail, right? So that means 57 ways out of 81 possibilities gives us 57 is 3 times 19, and 81 is 3 times 27. That gives us 19 out of 27 total ways, which is E. Nice. Okay, number 18. Which of the following does not evenly divide 90 factorial? So this is a problem where we can't avoid casework. We need to check all of these, unless we find it right away, which number does not evenly divide 90 factorial. And what does that mean? It means that 90 factorial divided by a is like an integer, right? It has to be a whole number. So if 90 divided by a is whatever bajillion quadrillion 0.2, then a does not divide 90. But if it's just whatever billion quadrillion point nothing, right? No decimal, then we know it does divide. So 90 factorial, I want to note this, is also equal to 90 times 89 factorial. And if you don't know what factorial means, the exclamation mark, it just means if you have like 10 factorial, then that is equal to 10 times 9 times 8, going down by 1 every time, times 7, times 6, times 5, times 4, times 3, times 2, times 1. So you go down from that number by 1 every time until you hit 1, and you multiply them all together. That's what a factorial is. Okay, so it makes sense that 10 factorial equals 10 times 9 factorial, because this is 9 factorial, just like this is 8 factorial, right? So that's a cool property about factorials. Anyway, 90 times 89 factorial. 89 factorial. So if we divide that by, look at C, we have 89 factorial here. So if we divide, we're going to ratio to 1 with the 89 factorials. So those ratio to 1, and we're left with 90 divided by 3 factorial. So 3 factorial equals 3 times 2 times 1, which is 6. So 90 divided by 6, we don't even have to compute that. We just know it's divisible, right? It's divisible by 2 and by 3. So 90 divided by 6 is an integer. So we can rule out C as our answer. Okay. Is there anything else we can rule out? So if you know what the choose function is, A, choose B, what that means is how many ways there are to choose B things out of A things. So like if you have 5 people, A, B, C, D, and E, and you want to choose 2 of them to make a group, right? So maybe that group is BC, or like AD or something. The amount of ways to choose that group is going to be, well, you have 5 options and then 4, right? Because you took one away. But also order doesn't matter, right? So BA equals AB. So we divide by 2. Okay, so 5 choose 2 is 5 times 4 divided by 2, which is 10. In general, n choose k equals n factorial divided by k factorial times n minus k factorial. Notice that there's always an integer number of ways to choose things. So like the choose function given two positive integers will always output a positive integer, right? Notice that if we pull up n factorial over k factorial times n minus k factorial, that will always be an integer, okay? Now, if we're looking at these two, notice that 42 plus 48 equals 90. So that means that we have 90 factorial over, for example, this one, 42 factorial times 90 minus 42, because that's 48 factorial. And we know that's an integer, right? That's 90 choose 40. 90 choose 42. There's an integer number of ways to choose 42 things out of 90. And it's the same thing over here, because 90 minus 24 is 66. So these two are ruled out because of that, right? So it's between A and B. One of these does not evenly divide 90 factorial. Okay, now let's think harder about what it means to not evenly divide something. So you should know about primes and prime factorization. A prime is a number like 2, 5, 7, 19. Numbers that if you want to make a grid with that many, like if you want to make a grid with exactly 7 squares, then the only way to do it is to have one long 5 by 1. There's no other way to do it, right? That's not 5 at all. At all, but still my point stands. So that's what a prime is. 2, 3, 5, 7, 11, 13. The non-primes are called composites, so 4. You can make a 2 by 2 grid, right? What that means is that 2 times 2 equals 4, right? So that means that a number other than 4 divides, or a number other than 4 and 1 divides 4, right? 2 divides it, and 2 is neither 4 nor 1. But no number divides 11 except for 1 and 11. So we want one of these numbers to not evenly divide 90 factorial. 90 factorial is the product of a bunch of primes, because every positive integer is a product of a bunch of different primes. Okay. So if we write a fraction with all those primes, like 2 to the power of whatever times 3 to the power of whatever, k1, k2, 5, k3, on and on until, I don't know, 89, is that prime? 89 to the k, whatever prime that is. So if we write that out as a fraction, the only way for either A or B to not divide 90 factorial is to be if one of those primes occurs more often in one of these numbers than in 90 factorial. And what primes could those be? Those could be like 2, maybe, probably not. 3, maybe. 4. 4 isn't prime, so no, definitely not. But let's think of like bigger primes. If we want a prime to occur more often in one of these than in 90 factorial, then let's think about something. 39 plus 53 equals 92. 31 plus 61 also equals 92. So they add up to the same thing. what does that tell us? That means that there has to be a prime that is closer within 2 of dividing one of these numbers, like 61 or 53, that occurs more often than in 90 factorial. Okay, so how many 13s evenly divide 90 factorial? How many 13s can we divide 90 factorial by? Just as a wild guess. Well, we have 13, that gives us 1, but then a multiple of 13 would be 26. And then another multiple of 13 would be 39. And then 52. And then 65. And then 78. And then we're at 91, so that's too big, right? So that means that we have 13 to the power of 6. That's what we can divide 90 factorial by and still have an integer. But if we divide it by 13 to the 7, then we won't have an integer anymore. We've divided it by 13 too many times. It doesn't have 7 factors of 13 in 90 factorial. There are only 6. Okay, 39. 39 gives us 39 factorial rather gives us 3 factors of 13, right? 1, 2, 3. But 53 gives us 4, right? We get 13, 26, 39, 52. So we have 4 factors of 13. So that means we have a total of 3 plus 4 equals 7 factors of 13. So if we were to divide 90 factorial by 39 factorial times 53 factorial, then we would be dividing it by 13 7 times. But we can only divide it by 13 6 times. So that means that our answer is A. So that's a really difficult problem. I mean, even if you eliminate all these answer choices, you still need to kind of guess what the prime is going to be just based on what you know about like multiples of primes. So this one, 31, if this was 62, right? If that was 62 instead, then we would have 3 31s, which would be too many, right? 3 31s don't divide 90 factorial, only 2 do. We get 1 from 31 and 1 from 62. But if we went again, we would be at 93, which is too much. That doesn't show up in 90 factorial. But we would have 3 in 31 factorial times 62 factorial. But since it's only 31 factorial times 61 factorial, we can't guarantee that. So the answer is A. Okay, question 19. A rhombus with diagonals of length 18 and 24. So this is what a rhombus looks like. And it says its diagonals are 18 and 24. So a rhombus is sort of just a kite shape, right? But notice that it's not like this. That's not a rhombus. A rhombus has to be symmetric about this axis and this axis. So it's symmetric about its both diagonals. Okay, and its both diagonals they intersect at right angles. That's good to know. And their diagonals are of length 24. That's going to be our big length. And then 18 will be our small length. So if we just look at a little portion, that means this would be 9 and that would be 12 in this like right triangle here. So what are we talking about? It has an inscribed circle centered at the intersection, which is right here, the intersection of that diagonals, and we're trying to find the radius. So an inscribed circle is going to look like this. And if we draw the radius, right, from the center of the circle out to where it hits one of these edges, then we know that that's going to be a right angle, okay? And notice that in this diagram, we've got this sort of situation going on, right? This is an altitude dropped in a right triangle. Whenever you have an altitude dropped in a right triangle, let's call these alpha and beta. Hopefully you know about similar triangles. So we have created three similar triangles here. And to prove that, we could think, okay, alpha plus 90 plus what equals 180? Well, by definition, alpha plus 90 plus beta equals 180. So that angle has to be beta. But then, what would that angle be? Beta plus 90 plus alpha would have to be 180. So that angle would have to be alpha. Okay? Alpha plus beta equals 90. And so that means that we have this triangle similar to this triangle, similar to this whole triangle. So if we divided, say, the longest side by the longest side of one of them, like let's look at this triangle right here. If we take its longest side and divide by its shortest side, then it would be the same as if we took this longest side and divided by this shortest side. And so in our diagram, what does that mean? So this is R. What is this whole length? Since we have a right triangle, we can just use the Pythagorean theorem, right? 12 squared plus 9 squared equals 225, which is 15 squared. So this is of length 15, right? So we have 15, 12, and 9. And we have our radius R. And we're trying to find R. We know that 15 divided by R, or sorry, no. We know that 12 divided by R is the same as 15 divided by 9, since R is the smallest leg in this, or it's the smallest length in this triangle, and 9 is the smallest length in this triangle, whereas 15 is the largest in the big triangle, and 12 is the largest in the small one. So that means that 12 divided by R equals 15 divided by 9. Well, that's the same if we flip this, as R divided by 12 equals 9 divided by 15. So then R would be equal to 9 times 12 divided by 15, which is, if we divide off a factor of 3 here, then we get 3 times 12 divided by 5, which is 36 over 5, or 7.2. So that's the length of our radius, and our answer is E. Okay, question 20. How many integers x are there, such that there is an all acute angled triangle with sides x, 12, and 15? What does an all acute angled triangle look like? Looks like this. All of these angles are less than 90. A different case would be if one of our angles is greater than 90. So we would have an obtuse triangle with an obtuse angle. Okay. So we want a triangle like this. And let's say the side is x, right? 12, 15. And this would work. But if it was like this, where this was x, 12, and 15, it wouldn't work, right? So this is good, this is bad. Where's the boundary between these two triangles? It would be, well, if you look right here and right here, notice that we're sort of swinging past a right triangle, if that makes sense. So we're swinging past if it was like this. This would be like if it's in the middle. That'd be x, and that would be a right angle, that'd be 12, and that'd be 15. Well, if this were the case, we would not have an all acute angled triangle, but we would just barely not have an all acute angled triangle. Like if x was any bigger, then it would have to be all acute angled, because that angle would shrink, right? That one would grow a little bit, that one would grow, but that angle would shrink. Or maybe, yeah. So how do we find x here? Okay, 15, 12, x. So 15 squared minus 12 squared equals x squared. 15 squared minus 12 squared is 81. So x is 9. So 9. So we know that if x is greater than 9, then we're in the right ballpark. But what if x is way big, right? Then that angle is going to become obtuse, right? Or that would have to be 15. Or maybe that would be x, and that would be 15, and that would be 12, right? If x is way too big, then it's not going to work. So we want to squeeze it down, do the same thing where we get a right angle here instead of an obtuse one. And we know that if x is smaller than that, then we're all good. So what would x have to be here? So 12 squared plus 15 squared equals 144 plus 225, which is 369. 369, that's less than 400, which is 20 squared. What about 19 squared? 19 squared equals, well, let's just compute this. It's 9, 1, 8, 9, 7. This is 361. So we know that 369 is between 19 squared and 20 squared. So x would have to be between 19 squared and 20 squared to make a right triangle. But remember, we want x to be an integer, and we want it to be less than whatever the square root of 369 is to get an all acute triangle. So that means x would have to be less than or equal to 19, because it could be 19, right? It could be less than or equal to 19. And then it would be it'd be greater than 9, or that's the same thing as being greater than or equal to 10. So now we just need to find how many x's are greater than or equal to 10 while being less than or equal to 19. So 10, 11, 12, on and on to 19. That's 19 minus 10 plus 1 equals 10 integers. So our answer is C. That's a tricky question too. That one probably tripped a lot of people up. You just have to know that the boundary between an obtuse triangle and an acute triangle is a right triangle. And if you know that, then you can sort of figure it out from there, because having a right triangle gives you enough information to solve for the third side given too, no matter which side you're given or which side you're not given. So these questions, this was probably, I would say, the hardest stretch. Looking over all of these, I mean, this one, it's okay. This one, I don't know. Well, our next stretch is more doable. I would say that 16 through 20 on the 2025 Fall Probe 1 was probably the hardest stretch in all of like that year's 5-question stretches. Like 16, sure, is super duper easy. 17 is a little bit tricky. 18, you need to really you need to do some figuring to get 18. And you need to do some lucky guessing, honestly. And you need to have really good number sense. Number 19. Number 19 was, I mean, if you know similar triangles, if you know what a rhombus is, right? Some people forget. Some people confuse it with trapezoid or like a parallelogram, but it's a rhombus. If you remember what that is from I don't know, Math Bowl or something, and you can visualize all that, then you can get it. Number 20 was also really tricky. So I would say don't feel bad if you weren't able to get any of these, or if you think that these ones are too hard for you. You just need to focus on those areas, right? And if you did focus on those areas, then after strengthening your problem-solving skills, you'd eventually be able to be comfortable enough to solve all of these. But anyway, that's all I have for you today.